Welcome! We are Claire Rumsey and Matthew McDevitt from York College of Pennsylvania, studying civil engineering. Together we're excited to present our research on the influence of Weir Nose Geometry on Broad-Crested Weir Hydraulics. Water is one of our most vital resources, and managing its flow is critical for both communities and ecosystems. Broad-crested weirs are essential hydraulic structures used in dams, spillways, and flood control systems. Broad-crested weirs control water flow to prevent floods, ensure steady water supply for various needs, and protect communities by managing downstream speed and volume. But not all weirs are the same. Small design variations, such as shape of the nose or its radius, can significantly impact how water behaves as it flows over the crest. These differences affect the flow velocity, water levels upstream, and even the efficiency of water discharge. Our experiment focuses on these geometric differences, specifically how bearing the nose radius of a broad-crested weir changes the flow characteristics in a controlled channel. To answer our research question, we designed an experiment to study how the nose radius of a broad-crested weir affects the upstream head, flow velocity, and discharge coefficient. We utilized the 2.5 meter flow channel, a hydraulic bench, and 3D printed weirs with different nose radii. In our experiment, we tested 6 different nose radii for the broad-crested weirs: 0, 10, 25, 40, 75, and 100 millimeters. When water flows over a broad-crested weir, fundamental energy and continuity principles govern its behavior. The surface level drops as water accelerates onto the weir crest due to the narrowing flow area. The total head H combines static and velocity heads above the crest, as described by the continuity principle and Bernoulli's equation. Real-world factors like friction, turbulence, and non-uniform flow cause energy losses. These are captured by the discharge coefficient C, which adjusts the theoretical discharge equation to calculate the flow rate Q. We then vary the weir's nose radius and flow rates to achieve different upstream heads, aiming to see how geometric changes impact water flow efficiency. To start our experiment, we connected the hydraulic bench's outflow pipe to the flow channel's inlet pipe, turned on the pump, and adjusted the flow rate to achieve specific targets, recording them with the bench's flow meter. We tested multiple weir shapes, some with no radius, other with nose radii of 10, 25, 40, 75, and 100 millimeters. For each weir, we focused on measuring water depths at specific points under controlled flow conditions. First, we placed the weir into the flume, centering it carefully. This position remained the same for all weirs for consistency. We measured the upstream water depth by using a depth gauge at a fixed spot on the water surface, then calculating the difference between this measurement and the upstream reference height. Next, we used the depth gauge to record reference heights. These measurements, taken at the start, middle, and end of the weir, serve as our baseline for comparing water depths during the experiment. We then measured the water depth at the surface at the start, middle, and end of the weir crest, relative to its corresponding reference height. To ensure reliability, we took 3 measurements at each position and repeated this process for 4 different flow rates. After testing one weir, we replaced it with the next weir shape. We repeated all steps, recording reference heights, adjusting flow rates, and measuring water depths. By keeping our methodology consistent, we ensured reliable comparisons between different weir shapes. The top graphs showing upstream total head and depth above the weir crest versus discharge illustrate that the smaller nose radii result in higher head and depth. This trend leads into the bottom graphs where the discharge coefficient, represented by the slope of the trend lines, increases with larger nose radii, improving hydraulic performance over the weir. This next graph illustrates the relationship between discharge and upstream velocity for different nose radii. Similarly, as expected, the graph shows us that larger nose radii consistently lead to higher upstream velocities for the same discharge. These graphs show how different nose radii on broad-crested weirs impact velocity distribution at different flow rates. Consistent trends appear across all configurations, with minor differences due to the changing nose radius. Overall, our findings confirm that the larger nose radii improve flow by reducing resistance. At low and high flow rates, the no-radius weir had a 4.9% and 6.08 higher upstream head difference than the 100 mm radius weir. Upstream velocity for the 100 mm radius weir was 16.4% and 16.1% greater at low and high flows, respectively. The discharge coefficient using total head was 8.61% higher for the 100 mm radius weir, aligning with expectations. Larger nose radii improve weir efficiency, reducing resistance and enhancing water management. Slight measurement variations in environmental factors could affect results. In conclusion, larger nose radii enhance hydraulic performance by reducing resistance and increasing upstream velocity.